So we've got the picture back up here. We've got forces drawn on it, all of that. Remember that we talked about the axle exerts a force on the crank, and what it does is it keeps F net equal to 0. It does not exert a torque. The reason it doesn't exert any torque is because it is at the pivot point. So, is it any distance from the pivot point? No, it's directly at the pivot point. That means it has no moment arm. And if there's no moment arm, it's not exerting any torque. It can't. But there's also no R. There's no nothing. It can't exert a torque. It doesn't have what's needed in order to exert a torque. It doesn't have it, okay? So,
does that go by the center of the torque?
What do you mean the center of the torque? It's at the pivot point. So like these aren't pivot point. These are just like, I have a dot drawn there because we have, that's where like your pedal would be attached. So the pivot point is right here in the middle of the whole crank. That's what everything's moving around, is the pivot point. Okay, so since it's at the pivot point, it's not any sort of distance from it. The application point is the pivot point. There's no torque to be had. Okay? So each of these other forces, though, the F1, 2, 3, 4, they're all going to exert torques, and their torques would be torque 1, torque 2, torque 3, and torque 4. And how we find net torque is the same way we found net force, and net of everything. We're going to add the torques. So we're going to sum the torques up. Okay? And that is net torque. And what do you guys remember from yesterday what torque is equal to?
R
cross F, which what does that mean? It's R F what?
Sine
R F sine phi. Okay, or phi, whatever you want to call it, phi, faux, fum, you know, the whole thing. Okay, so now from here, we've talked about net torque. The only important thing to remember about net torque is that the torques are going to add together just like forces do, okay? They're just going to add together. And remember, we're not concerned with, oh, does it go left, right, up, down? We're concerned, is it clockwise or is it counterclockwise? Which one's positive, clockwise or counterclockwise? Okay, which one's negative? Clockwise. Perfect. Okay. Josh, would you like me to leave this on the board so you can copy it? Or do you want me to? Yeah.
Oh, I'll just take a picture of it.
Okay.
Yeah, I'm gonna do that.
Go for it. Take pictures.
I don't have my notes on this video.
Do you guys know what the dress-up day is today for the teachers? We're supposed to dress how we did in high school.
You did in high school. You lived in Florida?
No, I didn't. But like most of my clothes were like very used and holy, and this is the holiest shirt that I have. Like I've got holes in the back and stuff.
Holy?
Yeah, I wore very worn down clothes.
I do not think clothes are blessed today.
I was known as being like a mixture of emo, grunge, and hipster in high school. That was my that was my rep though. It was rough.
I'm wearing what I wear in high school too.
Thanks, Ian.
I mean, I literally was a teenager 5 years ago, so it's not like too much has changed. Okay. I mean, listen, these are all clothes that I still own. I didn't have to go out and get anything, so. I got dressed this morning, and my husband's like, why are you just wearing what you wear on the weekends? And I was like, fair point, fair point. Okay.
I don't think either. I don't care about that. I don't care.
The only difference is I probably weighed about 40 pounds more when I was in high school. That's not pretty sight. Okay. Gravitational torque. That's what we're talking about today.
Yay.
Why does my face feel so warm? Okay, so our learning objective is to calculate the torque acting on a rigid body due to a gravitational force. So, what do you guys think gravity acts on?
Everything. Math.
It acts on everything, okay? And within, like, let's say gravity's acting on you, like your body. Do you think it only acts on your body as like a whole, or do you think it's acting on every single individual particle within your body?
Every individual particle.
Totally both, yeah, but it acts on every single particle. Gravity acts on every single particle in an object, okay? Now, does gravity exert an upward force or a downward force? We always draw it in which direction, upward or downward? We always draw it downward, okay? Who remembers what the force of gravity is equal to? What times what? mg. M stands for what? What are the units? G stands for what?
Gravity.
No.
Sorry.
Acceleration due to gravity. What are the units for it? Meters per second squared. Good job. Okay. So the only way they sort of change this up here when they're talking about it is they add little i's to show that it's on each individual particle. The I is standing for individual particles, okay? Now, you might be like, how does this relate to torque? Okay, so let's talk about how it relates to the magnitude of torque. So if we're looking at the magnitude of torque, it's going to be equal to d(I) mg. Who remembers from yesterday what the D stands for? Look at one of our little drawings. We said that a certain thing was called D. Huh? The moment arm, right? The moment arm, okay? So we need to make sure that D is what? Should it be positive or negative? What should D be?
Positive.
Positive, because it's a distance. So we're not worried about it. Distance isn't a vector, displacement is. This is just a distance, so it's going to stay positive, and it's an absolute value. So this number should always come out as positive, right? Should we ever have a negative number if we're doing absolute values? No, we shouldn't. Okay, so let's look at another picture. God, hopefully you guys don't roast me as much for this one. It's not really supposed to look like anything too crazy, honestly. It's supposed to, okay, that's actually what it's supposed to look like. So I'm happy with that.
Is that a painter's tray?
It can be if we want it to be.
Oh, yeah.
Okay, and here is its axle or its pivot point, okay?
Is that one of those art things?
Sure, that's why I just told Jacob, like it can be if you want it to be. Okay, so we're going to be looking at two particles on... We're going to be looking at two particles on this, okay? They're the little blue dots I made. And which direction did we say gravity always acts on stuff?
Down.
Down. Okay, so this is going to be our little force due to gravity vector. And we're going to call this one mass 1 times g, and this will be mass 2 times g, okay?
Calculate the change in the force of gravity due to the distance they are from the ground.
We're just looking at a picture so we can discuss it. Okay, now, the only other thing I want to mark on here is we're going to say that right here is our center of mass. Okay, that's going to be our center of mass where I put the little X. Okay. So we've got, I'm going to draw this line up from the axle. It's supposed to be straight. I know mine isn't completely straight. And then these up from our little particles.
What are these?
Okay, we're about to see. These are going to be representative of our moment arms, okay? So that we can just get the idea, these are drawn up so we can actually see what the legitimate distance is from our particle to our axle, okay? So this is going to be our first moment arm. What do you think we're going to call it? D sub what?
D sub I.
1, because it's mass 1, okay? And then this is going to be our other moment arm. What do you think we're going to call it?
D sub 3. 2.
D sub 2, okay? Now, if we're looking at this picture, we're going to see, let's talk about what kind of torque, if it's a positive or negative torque getting exerted on each of these. Okay, so think about which way is positive and which way is negative, right? Okay, so do we have a positive or negative torque happening here with mass 1? Mm-hmm. Mm-hmm. Guys, this is the first real coffee I've had since the beginning of December.
You don't drink coffee.
Wait, so
I'm not supposed to. I'm not supposed to have anything acidic, but I have
Why
special
was that?
pills.
is that because of your stomach or your teeth?
You have to have-
It has to do with my bladder.
Oh, never mind.
Yeah, it's not acid reflux. It's like,
I remember you telling us about that.
yeah, but I'm so excited. Like, I'm going to be riding a high all day. I haven't had caffeine either since December, and that was espresso.
My tea, my mom finally
So
got
excited.
me some it's really nice tea that I haven't had in years for my birthday, and it's really
You're
nice.
excited. That's good. That's good. Okay, so let's look at another little easel thing, okay? Well, not easel. What do they call it? The paint thing? It's not an easel.
Palette.
Bob Ross thingy.
The Bob Ross thingy? I don't think it's actually called the Bob Ross thingy.
It's a painter's tray.
I love calling palette.
It's called the 2-pin.
Okay, so again, we've got the center of mass. We've got the axle. This is the same thing, just smaller because I drew it smaller. Okay, so now we want to talk about if our force, let's say it's occurring at the particle that's at the center of mass. What are we going to make as our mass there? What would we call it? What do you think it'd be representative of?
MCOM.
Do you think it'd be the whole mass or just the particle of the mass if it happens at the center of mass?
Whole mass.
It's going to be the whole mass, okay?
So just M.
So we're going to call that like a capital M times G, okay? So if this is occurring at the center of mass, since it is the center of mass, it's going to be like the entire mass is getting acted on. So we pretend that the object's entire mass is at the center of mass when we're doing physics and when we're doing torque and all of that fun stuff. And our moment arm is still going to be right here. We're going to call this just D.
So that's why it doesn't have I. Or, no one.
Yeah, we don't need it.
Oh yeah, that's why I didn't put anything next to it. This M is just the whole thing. Just the whole
Like
thing.
The whole pizza.
Amazing.
No, you want-
Yeah, you can. It's like the whole mass. It's your whole mass, okay? Whole thing.
Like, yeah, like what?
Then what's the second Mr. Hall?
I can understand so good in my head, but I can't like explain things.
And then, so how we're gonna represent this, you guys? Right here, when we have this mass 1, mass 2 whole deal going on, we're going to say that our TI be negative XI MIG because T is going to be the opposite of whatever the X is. And then the net torque due to gravity. So this is just how we're going to find our torque. How we find the net torque due to gravity. And don't worry, I'm not making you guys derive any of this stuff, so be happy.
Equals to so much. Yeah, it's gonna be like the center of mass equation.
Who knows? Let's see.
It's the 2 grad. Because it's grad. What?
I don't know. I want to have it all right now.
Wow, look at that, Ian. We got that center of mass in there, like you said. So our torque due to gravity is going to be negative whole mass times G times the x center of mass. That's how we're going to find our torque due to gravity on an object.
Wait, so is x center of mass just your distance from the center of mass?
No. So x center of mass is going to be the positive of the center of mass relative to the axis of rotation or the pivot point. So it's going to be the moment arm right here. It's the moment arm between the axle and the center of mass. So here, I'll circle that and I'll write that. And then mg, of course, this is going to be the net gravitational force on the whole object. So I'll underline this and write moment arm between the pivot point and center of mass.
I just have a question.
Yeah, what's up?
Would the moment arm ever change even though the distance between them wouldn't? Like, what if you rotated it? Wouldn't that change the moment arm?
So you're saying like if now you had it like this.
And then the D would be longer. That was mine. Yeah.
Like that.
All right, we're gonna have to do like J1 moment arm.
I don't really think so. No. So remember, you guys, when we do this, we're gonna treat everything like what's located at the center of mass. Everything. All of our mass is located at our center of mass. So don't worry, we're about to do an example. Can I erase this to start the example?
Yes, ma'am.
No.
Here, I'm gonna take
I wrote it all down.
Dang, Josh, I'm proud of you, man. You're coming back.
There's another.
Oh, you don't need to worry about this one. This was just an extra one for Ian's.
Oh.
For Ian, yeah. All of this is on Google Classroom, yeah. It's already all posted. The notes for everything except angular momentum are posted. Because you guys, my AP class last year, they didn't get to experience angular momentum. It was sad. They didn't get there in time. Can I erase it now? Yeah? Awesome. Okay. How was the concert last night?
I was pretty good. Okay, yeah. This is the best time I've played.
What's not his purpose?
Okay, so we are going to be looking at the gravitational torque of a beam. Okay, so we have a 4-meter long, 500 kilogram steel beam. I'm going to put it up on the board. Don't worry, you guys will still get a ridicule drawing. And it's supported 1.2 meters from the right end. We want to know what is the gravitational torque about that support. So let's draw the picture. Here is our beam.
Oh.
Okay, that's our beam. Okay.
Yeah, that's about the same size.
This is our support. Okay. Now, we said that the beam is 4 meters long, okay?
It's about 1.5.
And we said that from the support, we are 1.2 meters from the right end of the beam. Now, please ignore that this is totally not drawn to scale, and I'm very sorry. Okay. Then, this beam is uniformly distributed, okay? So, from the center of mass to our support, it's going to be, huh?
1.8.
No, it's going to be 0.8 meters. I said this isn't drawn to scale. I did a bad job. Because think about it. Wouldn't the middle be at 2 meters?
Yeah, forgot.
So 1.2 plus 0.8 is going to be 2 meters. It's okay. It's okay. I did my drawing wrong, so you're fine. Okay. So let's think about this. So we have the center of mass at the beam point. And didn't we say that so first I'm going to write the equation for gravitational torque over here. You guys, what did we say it was? It was negative what?
Negative mg times X center of mass.
Oh, you guys knew it as I wrote it on the board. That's crazy. Okay.
Okay, I could've said
So-
it.
Now, does anybody remember how much I said this mass was of this? Do you guys remember? No.
500 kilograms.
Bam, good job. I said it was 500 kilograms. Okay, an X center of mass, didn't we say that's the distance, like the length of the moment arm? So how far are we from the center of mass to our pivot point?
20 meters.
And you guys, what's G?
9.8.
Woo!
That we are on Earth.
Is it negative 9.8?
Assuming that we are on Earth. No, we're just going to use regular 9.8.
Do all the questions say that?
Wait, why? Why don't we use negative? It's not,
Do you want to use negative?
doesn't matter.
We like negatives.
Okay. I'm guessing that's just
That
my
would
question.
make it toward positive value.
Yeah. Because they have,
Yeah, so you guys, what we need to think about, this is how we're going to figure out if our answer needs to be negative or not. If we are pushing on it this way,
yeah, it's going to be positive.
do we need to have a positive or negative answer?
Positive.
Okay, so isn't something in here going to have to be negative?
Wait.
What do you think is going to need to be negative? So we want it to be something that we get to decide if it's going to be negative or not. So like if we were to make it 9.8, we'd have to make it negative pretty much every time because G is something that stays constant, right? So do we make the mass negative? Is that a thing that we can do?
No.
So what are we going to make negative?
X center of mass.
The X center of mass. Why do you think the X center of mass is negative, you guys?
Because it's to the left of the pivot.
Because it's to the left of the pivot point. It's to the left of the pivot point, so we're going to make it negative. Sometimes I feel like it's best for us to learn these kinds of things in the example, so I think it's fun.
Yeah.
Okay, so that's going to be negative. Do we have everything we need to plug in to find our torque due to gravity?
Don't you mean substitute?
I said to find.
Plug
Do
in.
we have everything to find? Or
3,000.
okay, so we're going to say negative 500 kilograms times 9.8 meters per second squared times negative 0.8 meters. And it sounds like somebody else already found the answer. So what is it? 3,900 what?
20.
What are the units? Newton meters. Good job. Woo! Was that bad? Gravitational torque, did it hurt your soul?
Do we have to interpret that value?
What do you mean you have to interpret that value?
Like, I know in like math we have to interpret like what the value of it is.
That's when you're like doing integrals.
Yeah.
Yeah, this isn't an integral, this is just multiplication.
It just means that you're broke.
What if for like a word
It's an
problem?
Yeah, you're gonna have to do your problem. It's gonna ask for it very explicitly.
Okay, so why is the torque positive?
Because it's counterclockwise.
Yeah, because the gravity is trying to move it counterclockwise, okay? So that is why we are going to be positive. Oh, this is when I made them do a problem set.
Problem set time.
But we're going to go ahead and move on to static equilibrium and talking about static equilibrium, okay?
When we're doing practice, can we do a practice set for Q's?
Yeah, sure.
Every day.
So instead of doing, so I told you guys that I already assigned like 3 AP multiple choice questions to you for this week, right? So if you want to, instead of doing like a problem set in class, we can just do an FRQ together as a class. Okay?
Either one is.
But right now we're going to move on to static equilibrium. Because honestly, my biggest goal is to get through everything fast enough that not only we can review, but we can do at least one of the really fun labs that I have for rotation. So you get to like calculate torque due to like unraveling a roll of toilet paper. My students usually get really into it, so it's a good time. It's fun. It's fun. Okay, so static equilibrium. That's what we are talking about now. All right. anybody wants to do the problem set for practice, just for funsies, and then have me check it for extra practice, I'll let you guys know what the page number and numbers are for everything, okay? So, learning objectives for static equilibrium. What does AP want us to know? They want us to be able to describe the two conditions of equilibrium for an extended rigid body, calculate unknown magnitudes and directions of forces acting on an external rigid body that is in a state of translational and rotational equilibrium. So they want us to know the conditions of equilibrium, okay? So the conditions of static equilibrium are as follows. The sum of the forces, what do you think they need to equal to, you guys? 0. The sums of the torque, what do you think that needs to equal to? 0. Okay. And then finally, just to stress that both conditions have to be satisfied in order to be in equilibrium. That torque T is really bothering me. To be in equilibrium, both of these things have to equal what? 0. Okay, so these notes, if anybody's interested and wants to go and look back, they start on page 311 of your textbook. 311. Okay. So let's talk about this. If we have an object, okay, and let's say that it's completely stationary, that means that it's in static equilibrium. It's completely stationary. It's not doing anything. It has no linear acceleration. It has no angular acceleration. So that means no net force, no net torque. It's got nothing going on, okay? So no acceleration in any way, shape, or form. So I'm going to draw you guys a model of static equilibrium. Right? What's really cool is that since I'm getting to lecture this in class, though, you guys are getting the information at a quicker pace than the AP class in last year. So I am hoping that we can, have this time for you guys to review, okay? Because I don't know if your teachers obeyed it or not, but we were told we couldn't really assign anything over 15 minutes when we went to Learn From Home last year.
Yeah,
So they, my longest videos for AP, like I said, I never made them do over 18 minutes of work a day. Okay, so here in this picture, our acceleration is 0. Does this A represent linear or angular acceleration? Linear. Okay, this is where I asked, what do you remember from Paul Hewitt? Because we haven't done rotational kinematics yet because they want us to do torque first. Does anybody remember what the symbol for rotational or angular acceleration looks like? No, that was for angular velocity. It looks sort of like the Jesus fish. Right? Yeah, it's the alpha. Okay, and that is also equal to what, you guys? 0. Okay? They're both going to be equal to 0. So due to this, you guys, what is our net force on this?
0.
What is our net torque on this? 0. Everything is 0. And do you think that is only at certain points on here?
No, for the whole thing.
It's at every point. This is true at every point. Are you going to cry?
Because he forgot his AP stuff.
Oh, no. True at every single point, okay? So you can use any point at all, and what's it going to come out to? 0. Okay. Now, this model fails if either the forces or the torque aren't balanced. So they have to stay balanced, and the object must be at what? To be in equilibrium, the object must be at rest. It's not going to be moving.
It's a force and torque vector anymore?
Huh?
It's force and torque vector anymore?
Yeah, they're still vectors.
Okay.
I just didn't put the little thingies over them because I'm a bad teacher. Okay, so let's look at some examples. We've got a lot of examples that we can do for static equilibrium. I'll give you guys some options. Which one do you want to do first? We have one on lifting weights, walking the plank, and if a ladder is going to slip.
Weights. Pumping iron, getting built.
Do you even lift?
No.
Need it, son. I don't believe.
Lance?
I grind at 600 that melt.
I went to box.
Okay. So like, let's talk about lifting weights, okay, you guys? So weightlifting can exert extremely large forces on the body's joints and tendons. There's something called the strict curl event, okay? And in the strict curl event, a standing athlete uses both arms to lift a barbell by moving only his forearms. Nothing else, just his forearms, okay? Or her forearms. And where do those pivot at? Where do your forearms pivot at? Your elbows, okay? So you're pivoting at the elbows. The record weight lifted in the strict curl is over 200 pounds, which is about 900 newtons, okay? I cannot do that. So I'm going to draw a figure that you guys are going to make fun of the arm bones and the biceps as the main lifting muscles when the forearm is horizontal. We're going to solve for what is the tension in the tendon connecting the bicep muscle to the bone while a 90 Newton barbell is held stationary in this position. Okay? So, oh God, you guys are really going to remember this.
Is it the forearm or the tricep?
I have to focus, Ian. I have to focus.
Because it's only goes like down that way. Bro.
Yeah, these are bones right now, okay?
Oh, dear.
Listen, leave.
No, that's not. I'm not even funny.
What are the name of the bones? There's bones.
So those are our bones that we've got, and then
I'm just gonna draw sticks.
you're just gonna draw sticks.
Yeah.
Then we've got some muscles going on here.
You're a radius guy or more of a radius guy myself.
Okay. This guy is so built. Okay. And then we've got alright, that is way too far to the side. My goal is that as a physics teacher, I'll slowly improve my drawing skills.
Oh, you got stuff there.
I think it's just the association.
Okay, I am not going to try and realistically draw this hand because that would just take me way too long. So that's the hand. There we go. Okay.
Nice.
And then here we're going to draw a circle that represents the barbell. We're going to act like it's a see-through circle, okay?
That's huge.
It's like 200 pounds. Okay, so this right here is what we're going to consider our lifting muscle. And it is, what muscle is this, you guys? The bicep. Okay, that's our bicep. Now, what we're going to get from this picture is that from here to here is going to be, we're going to say that's 4 centimeters. And then from there to the center of this barbell.
Wait, why do you need to know the thickness of the muscle?
Shh, we're going to get there. You might not need it. You never know. They love to give you stuff you don't need, don't they?
Yeah.
And from there to the center of the barbell, we are going to have 35 centimeters, okay? This is the image that we are provided to go along with what I read, okay? So, 35 centimeters, yeah. So the first thing we need to do is sum our forces. Do you think we want to sum them in the y direction or the x direction? Let's start with the y direction, okay?
Yeah.
So let's think about what forces we have going on in the y direction. We have a force of a tendon that's working on everything. And so we're going to model the arm as two rigid rods connected by a hinge. Okay, that's what we're modeling this as. We've got rigid body connected by a hinge. What's our hinge? The elbow, right? Okay, so we're going to ignore the arm's weight. We don't care about it. We're going to act like it's negligible compared to the 200 pound mass it's lifting, because that's a lot less than the barbell, right? Your arm does not weigh 200 pounds, correct? Does anybody's arm weigh 200 pounds? No? Okay. And we're going to be, stop. And although the tendon pulls at a slight angle, we're going to say it's close enough to the vertical that we're going to treat it as such. The tendon's acting like it's just vertical, okay? So we're going to have the tendon minus the force of the elbow minus the force of the barbell.
So the tendon would be acting like 4 centimeters out from the joint.
Yeah. And what is this going to be equal to, you guys?
0.
0. Okay. Everybody make sure you have this down. It's where we're going to start tomorrow because the bell's about to ring. But what's going on here, you guys? The biceps pulls the forearm up against the upper elbow. So the force of the elbow on the forearm, at the elbow, all that stuff, it's a downward force. And since, why is it all going to equal 0, you guys? What's it in?
Equilibrium.
What kind of equilibrium?
Static.